So this video, I'm going to do examples of volume using washers and shells so that we can compare the two techniques. So before you watch this, I would strongly recommend that you have done some problems with washers and done some problems with shells so that you're at least familiar with both techniques because I think otherwise this is just too much information to pile on top. Okay, so first of all, let's just remind ourselves, what is the difference? So with washers, we're using cross sections, and you need to know what the outer radius versus the inner radius is. And I'll demonstrate this as we kind of go along. So the formula, so if you're going around the x-axis, you're going to integrate with respect to x. So I take pi times the outer radius squared minus the inner radius squared. And then if I rotate around the y-axis, it's the same formula, but everything's in terms of y, okay? Now, compare that to shells. Shells are not cross sections, right? We think of shells as they're this rolled up thing that I could unroll. That's what a shell is. So the formula is actually a volume formula because we're literally finding the volume of a shell. So in this case, so it's 2 pi times the shell radius times the shell height dx. So notice this. We integrate with respect to x when we go around the y-axis. And then we integrate with respect to y when we go around the x-axis. So just notice, right? So there's actually like, they're kind of like flip-flopped, right? So with cross sections, we integrate with respect to x around the x-axis. With shells, we integrate with respect to x around the y-axis. So if it were me, I'd probably put all of this down on one piece of paper if you're struggling with this, and I'll flash these up again and you can pause the video if you so desire to write this information down. All right, so that being said, we're going to do a problem just kind of comparing everything. So I've got this region and we're going to revolve it and use different methods every single time. So you can pause and read about it if you so desire, but I'm just going to jump right into this. Okay, so I'm going to start by calculating the volume revolved about the x-axis using the washer method. Okay, so first things first, we have to know what is this region that we're talking about. All right, so here's 1, and then, see, I'll go up 1, over 2, maybe I'll go up 1, over 2. Okay, so I've got one curve here. There's one curve. Okay, and then my other curve is just y equals x, so that's going to be up 1 over 1, up 1 over 1. Okay, and then the last curve will be x equals 0, so that's this curve right here. So we're talking about this little region. So let me just redraw that real quick with that blown up now that I know what we're looking at. Okay, so I wanted to just have a nice visual of the curve, nice and cleanly drawn, so I did that. Okay, so next I need to revolve this about the x-axis. So I'm revolving this way. So I think it's also very helpful to know what your solid or what your shape looks like. It doesn't have to be like perfect, right? So I've got something that looks like this, and I'm just going to revolve it around this way, I guess. So I've got this like hole in it. Okay, so this is solid out here, this is solid here, and then we've got this big divot in the middle. Okay. So since I've rotated around the x-axis, what formula am I going to use in this case? Well, I'm going to be using this one. I'll just put it on the screen. So I'm revolving around x-axis, so I'm going to integrate with respect to x. So for this one, then this is actually pretty straightforward. This is nice. So I really just need to know what my outer radius and my inner radius is, and from this picture I can very clearly see here's the outer, so that's this curve here, and then here's the inner. So I can just plug those in. And then, so my x's in this case go from 0 to 2. So 0 to 2, and then I can just plug everything in. So it's 1/2 x plus 1 squared minus x squared dx. Okay, And so then from there, so we're just going to integrate. So let me make a little space for that. Okay, so from here, you know, I'm just going to go ahead and show the steps so that I'm not taking up the time in the video. So if I go through and if I FOIL this out, so I'll show you what you get. Okay, so if I FOIL this part out, so I've got 1/4 x squared plus x, because that's 1/2 x plus 1/2 x, and then plus 1, all that minus x squared. So this will simplify to what you see here. And then if I integrate, so I'll get this result here. And then if I plug everything in, I'll get 2 pi. Okay. So that was using washers. And so remember, so I just want to remind you also, so when you do washers, so we're using a cross section. So literally, what does this cross section right here look like? It literally just looks like a circle. That's it. So it's a cross section, and we're just finding the area really then of this circle with the outside minus the inside radius. So, okay, that's the first one. Okay, so next, now I want to revolve that same region around the y-axis using the shell method. Okay, so let me bring back that region. So now I want to revolve this way around the y-axis. So just to kind of get a little idea of what that looks like. So now I've got something looking like this, and now I want to use the shell method. So remember, with the shell method, so when you rotate around the y-axis, you integrate with respect to x. So our formula will be this right here. Okay, so my a and b are still 0 and 2. And then my shell radius, so you can just find that by taking x minus the line that you're rotating around, which in this case, since I'm just rotating around the axis, the shell radius will just be x, that's it. And then, okay, so the shell height, so the height of this curve, I think it's always helpful to like draw lines of what height are you talking about. So let me get rid of the filling in there. So notice like these little green lines that I'm drawing here. These are the different heights that I'm talking about. And so this can really be found then by taking the top curve minus the bottom curve. So that's what's going to give me the shell height. So that's going to be 1/2 x plus 1 minus x. And so now we're off to the races again. So that's what I've got. So I'll make some space. Okay. So let me just simplify this, I guess. So I'll just show you the steps. So when I multiply, when I add all my like terms, so I've got 1/2 x minus x, that's going to be negative 1/2 x. And then when I multiply everything together, I've got negative 1/2 x squared plus x. So now if I integrate, so what am I left with? This is what I'm left with when I integrate. So let me just show you what it looks like then after I plug everything in. Okay, so you can see what's left of my work. So ultimately I get 4 pi over 3. Just as a reminder, if you're watching this, I strongly recommend, just so that you get the extra practice, that you're doing these integrals on your own, and then you're just kind of using the video to check your answer. That's the best way to use these videos. Okay, so same curve. Now we're going to revolve it around the line x equals 3 using the shell method. So once again, we just want to know what we're dealing with here. So let's bring back the region. Okay, and so in this case, so I'm revolving around x equals 3. So that line is over here. So let's draw this green line. So that's what I'm revolving around. So this is a vertical line. If I wanted to just draw a little sketch of kind of what that looks like. So I've got this shape here revolving around this. So I guess I'll have like this, let me draw a little line, this shape. Okay, so I've got something that looks like this, big hole in it. So since it's got this big hole in it, we can just use the cylindrical method. Okay, so now, since I'm revolving around this vertical line, so I'm still going to use, so am I going to integrate with respect to x or with respect to y? So still with respect to x, right? So I'll just put the formula up. Now what I would recommend here is, I think we've kind of gone through a lot of the technique here. So I would strongly recommend that you at least just try to set up the formula on your own and then hit play when you're ready. Okay, so I need to figure out the shell radius. So in this case, so I'm thinking of this as like, so I'm some value on this curve. So this curve, it could be anywhere on this curve. So this value will be x. And this value here is 3. So how do I measure this length? Well, I just take the top minus the bottom. So that's going to be x minus 3. This still goes from 0 to 2. So that's going to be the radius. And then the height will be the same thing as before. So the height of this depends where you are on the curve, but you've always got this top curve minus the bottom curve. So highest minus lowest. So that's going to be 1/2 x plus 1 minus x. Okay, so there's your setup in that case. And, okay, I'll make some space and I'll show you the solution. Oh, I wrote this down wrong. Sorry. So this is the higher value minus the lower value. So this is 3 minus x, my bad. So you always want to take the most right minus the most left thing. So, okay. So this is, so I'll go back to this, making some space. Okay, so now this is going to just require a little bit more work. So I'll go ahead and I will FOIL all this out and I'll show you all the steps. I strongly recommend that you just try to finish this integral totally on your own, and let's see if you get the same thing. It's a really good time to test your integration skills. Okay, so this took me quite a bit more work to FOIL all of this out, and I've got these fractions, but when all is said and done, so here's the product of multiplying these two things together, so you can check your work against mine. So now I will make a little space, and so I'll go ahead and show you what happens after I integrate. So here's my antiderivatives, and then I'll just go ahead and plug everything in, so I get 14 pi over 3.